Hello, a great welcome to Idea Statica tutorial. Myself is Jarajan P. This is tutorial number 22. Here I will demonstrate the modeling, analysis and verifications of a bracing connection which utilizes a shear plate. The code checks are done using the AISC-LRFD provisions. The scheme of connection used in the tutorial is shown in the figure. It essentially consists of a beam with a sharp welded gusset having punched holes to receive the bracing, which is directly bolt connected to the columns at site through the shear plates. The column is provided with stiffeners at 3 locations on one side. So let us start Idea Statica tutorial number 22. Please note that the link for the playlist for all the previous tutorials is given under the video description. So the model developed for this tutorial is shown here. So let me quickly take you through the various commands and the manufacturing operations used for the generation of this model. So let us straight away start with the members. So the member M1 as shown here is a vertical column that is a W14 by 120 and it is a geometrical type is selected as continuous and the vertical member, so the pitch angle is selected as 90 degrees and a NVM model is selected for the supports. And now coming to M2 as you can see that is a B member, so that is a W18 by 40 cross section is selected, and as the beam the geometrical type is selected as centered for one side and the beta angle is taken as minus 90 degrees, and this beam is positioned at a distance of 215 mm from the center line of the web so that it clears the flange. And for the beam as well we have selected an NVM model, and here I would like to tell you one very important thing for M1 and M2, so that is for the column as well as for the beam sections we have selected a steel grid of A992 and the properties of which can be easily seen, so get press OK. And now coming to M3 is your double angle member, so let me just edit it. So it's a double angle member with a size of 200 by 100 by 14 thick, and as you can see that the distance between the faces of these two angles is kept at 25, and the steel grade chosen here is different, and 886 grade is selected, so that's okay. And here the beta angle is kept as a minus 90 and the pitch angle, that is the bracing member, is kept at 45 degrees and the alpha rotation is kept at 180 degrees, and we have kept an offset distance of 675 so that it can be properly placed in the gusset. And here again we have chosen an NVM model, so that is regarding all the members. We have got 3 members, that's a column, beam as well as a double angle member for the bracing member. Now let me take you through the various manufacturing operations. The first manufacturing operation is the stiffening plate. So the stiffening plate manufacturing operation is used for the development of this gusset as shown here. So let me just, so this is the gusset that is being modeled, so we can just rotate it a little bit. Yes, so this manufacturing operation is the stiffening plate is this one as shown here, stiffening plate. And please remember that all these manufacturing operations are covered in detail in the previous tutorials. So accordingly, only a brief review of these manufacturing operations are provided here. So here for the SP1, that is as highlighted here. So the material grade that is chosen is a plate 1. So it's a A572 grade 50 material is chosen and the thickness is 25 mm. And it is basically chosen as a rectangular one with all its dimensions being prescribed through the B1, B2, H1 and H2 parameters. And it's connected with the member M2, that's a beam as shown here, and it is connected with the top flange of the beam, and the type is chosen as the rib with the location on the front, and the rotation is kept as 90 degrees. And here we will not be specifying the wells. The wells will be specified through the plate cut command. So here one more thing I want to tell you, as far as this SP1 is concerned, all these beveled edges are generated through the editor command. So if you go to the editor command, you can see that there is a bevel command here. This is the bevel command that is used to generate the chamfered edges. All right. And let us go for the next manufacturing operation, which is again a stiffening plate. So here you can see that this SP2, that is the stiffening plate manufacturing operation, is again used for the generation of this shear plate. Look here. So this is my shear plate, and this shear plate is connected to, let me just zoom it a little bit. Yes. So the shear plate is connected to the web of this column, and the shear plate assembly, it directly receives the beam along with the gusset. Okay, and please remember that this is a very simple arrangement. And here what is normally done is that this beam, it will be okay. There is a gusset plate. It will be welded with the beam in the shop. Okay, and this gusset will be having the punched holes on its body at the specified locations. And then what is done is that the beam along with the gusset, it is connected with the column, okay, which is already provided with a shear plate in the side in the weld. Okay, and then what is done is that this is shear plate, it is connected with the beam using the bolts. Okay, so SP2 is again a stiffening plate command that is used for the generation of the shear plate. As you can see that the material grade is A572 grade 50, and it's a half thickness at 25 mm, and its dimensions are being prescribed through the various B1, B2, H1, H2 parameters. And here we have kept the excess 25 mm, so that the purpose is very simple. We want to ensure that, okay, this particular shear plate, it is one surface of it is a flush, or it is in alignment with the gusset plate, so that they can be directly bolted. And then the Y is preset as minus 400 mm, and its RY is kept as 90 degrees. So through the stiffening plate command SP1 and SP2, we have generated the gusset plate as well as the shear plates. Now we have to pick up one command. So this cutoff plate command. So as you can see that it is the cutoff plate command is this is the cutoff plate command, and this is basically used to develop the welder connection. Okay. So for example, here pcut1 command, the manufacturing operation is used for connecting SP2, that is the vertical shear plate, with the column web. And as you can see that here we have used a full penetration butt weld. Okay, so that is we are talking about this connection, that is the connection of this shear plate along with the column web. Okay, so similarly what we can do is that we can use the same pcut2 command, that is again the cutoff plate command, to specify the welder connection between the gusset plate as well as the beam M2. This is what is shown here. The modified item is SP1, and it is cut by the top flange of this beam member. And as you can see that what we have used here is a double-sided fillet weld of size 8 mm. So this is the weld that is being generated, and as you can see that the weld is provided on both sides. So this command is used to specify the welder connection between the gusset plate as well as the beam top flange. So let us go for the other manufacturing operation, that is the OPN, that is nothing but the opening manufacturing operation. So let me just show you this manufacturing operation. So this is the opening, and this particular opening command manufacturing operation is used. Let me just zoom it. So here as you can see that there is, so let me just rotate it a little bit. Yes, so here you can see that this is the top flange of the beam, and on the same side we are having the what we call as the shear plate, and we have to make a notch in the beam flange, so that the shear plate can be properly accommodated in the beam M2. So this is what is being shown through the opening manufacturing operation, and as you can see that this opening is made in the M2 top flange, and the shape selector is the notch one, and the dimensions of the notch are prescribed through these parameters BH, B1 and H1. So we have generated a notch in the top flange of the connecting beam, and this notch is generated only on one side, as you can see. Yes, so here it is continuous, and this notch is created only for one side of the top flange of beam M2. Now let me take you to the other manufacturing operation, that is the GRD1. GRD1 is nothing but it is the bolt anchor grid manufacturing operation. So here you can see that this operation is, yes, so this is the bolt grid manufacturing operation, and this bolt grid manufacturing operation is very efficiently utilized to model all the bolts that is connecting the shear plate with the gusset plate as well as with the beam web. So let us see what GRD1 does. So GRD1, it provides bolted fasteners, and that we have two items. That is, the item one is SP2. SP2 means it is our what we call as the shear plate, and M2 web. So this is the M2 web. So basically what is done is that, so this command GRD1 is used to describe or to develop the bolts that is connecting the shear plate with the web of the beam M2. So as you can see that here we have specified the items very clearly, SP2 and M2 web 1. And the fastness type that you have selected is 24 mm A325M bolts, and the location and the numbers of the bolts are being prescribed through the rows and positions command, and the shear force transfer is assumed through the bearing tension or shear interaction. And then we have got another bolt grid command GRD2. As you can see that here again we want to connect two members, that is, but in this case we want to connect SP to the same shear plate but with the item SP1. So what we want to generate here is we want to generate the bolts that is connecting the shear plate with the gusset. So all these bolts are being generated through the bolt grid GRD2 command. So as usual, we have assumed the same 24A35 mm bolts, and the numbers and the positions are being prescribed through these parameters, and the same shear force transfer is assumed through the bearing tension shear interaction route. So we have populated all the bolts connecting the shear plate as well as the beam and the gusset plate. Now let us see how to generate the bolts connecting the double angle with the gusset. So this is being done through another manufacturing operation. Here we have not used the grid manufacturing operation because it is difficult also, and is so accordingly there is a very simple manufacturing operation that can be used to connect the members that are inclined. So this is the gusset. This is the gusset plate manufacturing operation, and here what we did is that we have used this manufacturing operation in order to populate all the bolts connecting the double angle with the gusset plate. So let me quickly show you what this manufacturing operation is. This is your manufacturing operation. That's a gusset that is specifically used for the truss members, and we have used the same here. And as you can see that this requires some parameters to be filled up. So remember, obviously this gusset is is on. That means the connection is to be executed for the member M3. And it has to be connected to the existing plate, and this plate to be connected is the SP1, which is written here, and the gap we have kept as 150 mm, and the bolts that we have generated will be using the same 24 mm A325M grade, and all the rows and positions are specified through these parameters, and the shear transfer bearing mechanism is assumed to be the same. So we have populated all the bolts connecting the double angle tension bracing member with the gusset plate. So finally we need to generate some stiffeners, and so let me just tell you one very important thing. As can be seen here, so what is done is that all the horizontal component and the vertical component of the bracing forces as well as the beam shears and axial tensions, these are transferred strictly through this shear plate. So what is important is that this shear plate is solidly connected with the column member. So if we don't provide the stiffness, there is a very possibility that a larger development of stresses as well as the strains in the column web. So in order to limit these quantities as well as the excess stresses and the strains, it is very important that we provide the properly designed stiffeners along the column length. So let us generate the stiff one. So as you can see that this is stiff one manufacturing operation. So this is shown here. So this is your stiffener. Yes, a stiffener manufacturing operation, and this stiff one is used to generate the the column stiffeners that are in alignment with the beam flanges. So as you can see that these stiffeners have to be provided on M1, which is a column, and their positions are related to the beam member M2. And we are providing to both the top as well as the bottom flange locations. So we have selected both, and here as it's again a plate, we have preferred to select an A36 material. We don't require a very high grade material here because these are basically used to develop proper restraints and the stability to the column web, and thickness we have kept it as 12 mm, and the location is the front. Okay, and here as you can see that the welds that we have used to connect the stiffeners is a double-sided 6 mm fillet weld. Okay, and now we have got another stiffness plate manufacturing operation, stiff 2. Okay, that is essentially used for the generation of this top stiffener. Please ensure that this top stiffener clears this shear plate and it creates no no falling at the site. So this is the the stiffener plate generated through the stiff 2. As you can see that this is on column member M1, and there is no related members, and the material is A36, and we have selected the same thickness 12 mm, and its exposition is conveniently fixed at 1000 mm, so that is just clears the shear plate dimensions. Please remember that before generating any model in Idea Statica, you have to make a very good sketch in your notebook. Okay, ensure that these are being properly positioned, and this is also one way to check whether the members are being properly positioned in the Idea Statica model. Okay, and here again as you can see that we are using the same double-sided fillet weld of a 6 mm. So thus our model is complete. It's a very simple model, but actually this model is a little bit interesting because you might not have seen this kind of a model with a shear plate, but this shear plate model is very convenient, because in this case what is done is that normally, based on my experience, what we do is we just take the beam along, okay, with the gusset plate that is welded in the shop, and then we have the column, okay, which comes again from the shop along with the stiffness and the shear plate. So what is required is, at the site you need to just bolt, okay, just to place these bolts in order to make any kind of a welding anything. So this is a faster one, but the very important thing is that in this case, as the entire load is transferred to the shear plate, ensure that it is having a sufficient thickness as well as the rigidity, and also it is connected directly with the column web. So accordingly, ensure that if you find a very larger concentration of stresses in the web, normally from my experience, what we do is that we also provide a what we call as a web splice plate, a web plate here on the back side, to strengthen the web. Okay, so that's all about the model generation. Now let me take you through the load effects. So look here. Here what we did is that we have applied, okay, we have loaded the members M2 and M3. That is, we have applied, for example, M2 is a the beam member, and we have applied a 300 kilonewton in compression. So it is being shown here. It is a compression of 300 kilonewton and a shear of 100 kilonewton. And we have got the M3 end, that is this is a double angle member. It is subjected to an axial tension of 1250 kilonewton. So here one very important remark is that here we are using the so-called LRFD approach. So accordingly, please ensure that all these member reactions or the member forces are to be taken corresponding to the factored load combinations given in AISC, okay, LRFD 2016 approach. Okay, maybe that you will be using a factor of, for example, 1.4 or 1.6 with the dead load, live load, and with the wind load, okay, probably we provide a factor of 1 or 1.1. So all the factored load combinations prescribed in the LRFD code has to be taken, and the member forces obtained from the analysis software, such as, say, for example, the ETABS or SAP 2000, has to be imported here corresponding to the factored load combinations, because we are using the limited because the limit state, okay, wherein the factored loads are being used and the materials are taken to their limit states. Okay, that is very important. Okay, so I think that with this we can straight away go for the analysis. So we just press the calculate button. So as you can see, our analysis is complete. Okay, it is performed for 100% of the loads. We find that all the components are looking pretty good, with the plates being taken a little bit higher strength of 0.8%. The bolts are having a utility ratio of 0.64%. That's okay, and the welds have been taken to 0.85. So overall, all the components looks pretty good. So let us go a little bit deep into the results. So the analysis, it is indicated as 100% is complete. Now regarding the plates, as we have seen, it is taken to a strain level of, say, 0.8%. Let us see which are these critical plates. So what we do is that we just sort out these things in the order. So the first one is 0.8%. So here we find that it is the item SP2, that is a shear plate. As I already told you, this is the main component that is transferring the entire loads to the column. So obviously we expect a larger strain concentration in this plate. So as you can see that here, this is the larger stress that is developed in the extreme corner of this, the shear plate, and that is gone up to say 0.8 percentage. This is what is being shown here, and you can also see this in the model. Look here, this is the strain of a 0.8 percentage that is developed in the shear plate, and we have a little bit comparatively lower strain levels being developed. For example, here we can say that it is developed in the M3 web 1. Okay, so that means we have some strains that is developed in, as you can say that in the web. See, in the web of this angle, we find that some kind of a stress accumulation in the outer edge, okay, as is shown here in the model and also shown in the component detailing here. But that is a 0.4%, that's okay. And we also expect the same thing on the other side also, that is M3 web 2. And the strains in the other models are the stiffeners, except they are of the very low margin, that's 0.2%. So now, having seen the plate, let us quickly go to the boards. And here I would like to tell one very important thing. So when we do the design or the detailing of such connections, we assume that the boards will be subject to the shear, okay, and they fail either the shear failure in the shank of the bolt material or the bearing. But here, if you see the Idea Statica result, look here, we are finding some kind of the tension also. Obviously, these are tensions that cannot be taken care of in our hand calculations, and these are generated because of the out of plane deformations of the plate, which causes the extensions in the bolt body. So, but we find that these are of a smaller magnitude. That's a 44.2, 44, 40.3. So if you see the bolt, you will find that this is one bolt which is subject to the maximum. It's obviously expected because of the outer plane deformation of the plate, and the other one is the outer bolt that is connecting. There's an angle with that gusset. So, but we find that these are of a smaller magnitude, and these tensions are getting reduced. You know that they all are of the order of say 10, 6, 5, 2, 3, because in those zones we have got only a smaller outer plane deformation of this plate. Okay, now let us see the shear. So these are the shears that is being developed. So you find the maximum shear being 80.1, and here we have seen that this as the tension, as you can see here, it is so let me just put it as here. Okay, so the maximum utility ratio in the tension is only of the order of say 21.3, so that is less than 30. So you'll find that there is no accordingly there is no interaction check between the tension and the shear in this column, that is kept blank because it's less than 30 percentage. And here is shown the utility ratio of the bolts based on the shear. So let me just see. So here we find that 63.5 is a maximum utility ratio for the bolt in shear. This is what is being reported here, so 63.5. So let us quickly identify which bolt it is. So this is, yes, this is the bolt which is connecting the angle with the gusset, that is being identified as this bolt. And as you can see that this bolt is subject to a maximum shear of say 80.1 kilonewton, and in bearing we have got a very large capacity, there is no problem as such. So but let us quickly see the kind of the explanation given in the Idea Statica calculation. So wherein you would find that it has made the tension resistance check based on the AISC 360, and here this is due to the yielding of the bolt shank, wherein we have used a yield stress level for the bolt of 620 MPa, and using a resistance factor of 0.75, we find that it is very much. So the tension resistance is 210.2. Okay, the tension resistance, and we find that this is less than 14.4 for this bolt. So there is no effect of the tension forces, and further this calculation also provides us the shear resistance check, and here the shear resistance is derived from the consideration of the shearing of the bolt shank and also from the bearing criteria. And here the calculations made from the AISC criteria shows that we have got a shear capacity of 126.1, and this is very much higher than the maximum shear of 80.1 kilonewton. And here a check for the bolt for the bearing is also being done in Idea Statica, and here we find that the capacity in bearing is very much higher to 41.9, so we don't have much concern from that side. So that is all the details given in Idea Statica regarding all the bolt checks as per the AISC. Now finally coming to the wells, we find that here that the wells are being taken to 84.6. So let us quickly identify which weld is this one. 84. Yes, is this weld? That is obviously we find that it is connecting. Yes, let us just see this one. So we find that it's connecting the stiffener with the column web. Okay, so that is being clearly identified, and it is that critical. Okay, that is the weld. That is a we have provided the fillet weld connecting the stiffener with the main column web. Okay, that's a critical as per the calculations performed by Idea Statica, and that works out to be 84.6%. So if you want to obtain a detailed report, go to the report section so that you can see a consolidated summary of the results. And I would recommend to the users also keep a copy of the AISC. And one of the most important thing is that you must be able to assimilate all the calculation procedures implemented in Idea Statica to see that okay, the calculation results are acceptable. So here you will find that all the result summary is presented in terms of the stresses, strains, everything, the total stresses and the bolt checks, everything all are given, and the corresponding forces are also marked over here, and the detailed calculations are also furnished here. So that is all about our result review. So please subscribe to the channel, because we are going to upload as many as very challenging and the real practical problem connections into the Idea Statica tutorial. So please ensure that you get a notification in future. Okay, so thanks a lot for listening. Have a nice day.